Picture this: a machine that can write poetry, compose music, and create breathtaking art from a simple text prompt. An intelligence so advanced it can pass the bar exam, write complex code, and even design new drugs. Now, ask that same machine a simple grade school math problem, and watch it fail spectacularly. This isn't a hypothetical scenario. It's the strange reality of our most advanced artificial intelligence. We've built digital brains that can mimic human creativity and knowledge in astounding ways, yet they often get stumped by the kind of arithmetic you'd find in a fifth-grade textbook. They can write a sonnet about love, but ask them to solve a word problem with a slight twist, and the whole system can come crashing down. This bizarre limitation isn't just a funny quirk. It's a crack in the very foundation of modern AI, revealing a deep and fundamental difference between human-like intelligence and genuine understanding. We're not just talking about complex calculus here. Even simple addition and subtraction can sometimes go haywire. So, what's really going on inside these powerful models? Why is math their Achilles heel? The answer is far more fascinating than you might think. It has to do with the fact that these AIs aren't really thinking at all, at least not in the way we do. And to understand why, we need to peel back the layers of the digital mind and look at what it's actually made of. At its core, the AI that powers tools like ChatGPT isn't a mathematician. It's a linguist. A very, very good one, but a linguist nonetheless. These systems are called large language models, or LLMs. And that name is incredibly revealing. Their primary function, the very purpose of their existence, is to process and predict language. Think of it like an incredibly advanced version of the autocomplete on your phone. When you type, "The cat sat on the ... your phone suggests Matt, because it has analyzed billions of sentences and learned that Matt is the most statistically probable word to come next. LLMs do the same thing, but on a mind-bogglingly massive scale. They've been trained on a colossal amount of text and code from the internet, and they've learned the intricate patterns of human language. So, when you ask an AI, "What is 2 plus 2?" it doesn't reason about the abstract concept of numbers and addition. It doesn't access an internal calculator. Instead, it scans its vast database of text and thinks, in the billions of examples I've seen, the sequence of characters 2 plus 2 equals is almost always followed by the character 4. It's not calculating, it's pattern matching. It's giving you the most statistically likely answer based on the data it has seen before. This is why they can seem so intelligent. They can hold conversations, explain complex topics, and write essays, because they are masters of predicting the next most plausible word in a sentence. But this also exposes their greatest weakness. They don't understand the concepts they're talking about. They are, in essence, expert mimics. And as we'll see, this reliance on mimicry is precisely what causes them to fail so spectacularly when faced with true logical reasoning. The old saying, "You are what you eat," is just as true for AI as it is for humans. An AI model is only as good as the data it's trained on. And when it comes to mathematics, the training data for most LLMs is surprisingly sparse and often flawed. Imagine trying to become a math genius by only reading novels and poetry. You might pick up a few things here and there, but you'd be missing the fundamental building blocks of mathematical knowledge. This is the situation that most LLMs find themselves in. Their training data is overwhelmingly linguistic. It's articles, books, websites, and conversations, all expressed in human language. While this data contains some math, it's often not in a structured, logical format. And more importantly, the internet is full of mathematical errors. Humans make mistakes, and those mistakes are captured in the training data. The AI learns from our errors just as much as it learns from our correct answers. So if a particular type of math problem is frequently solved incorrectly by humans online, the AI might learn to reproduce that same error. This lack of high-quality structured mathematical data means the AI has a limited grasp of advanced concepts. It might have seen enough examples of simple addition to get it right most of the time, but it's unlikely to have encountered enough data on complex algebra or calculus to truly master them. This creates a fragile foundation for the AI's mathematical abilities. It's like building a skyscraper on a foundation of sand. It might look impressive from a distance, but the slightest tremor can cause the whole thing to collapse. And as we're about to see, it doesn't take much to create that tremor. So, what happens when you take an AI that relies on pattern matching and has been trained on incomplete data, and you throw it a curveball? The results are, as one study from Apple researchers put it, catastrophic. In this study, researchers took a standard set of grade school math problems and made very slight changes to the wording. They didn't change the underlying logic of the problems at all. In one set of experiments, they simply rephrased the questions. In another, they added a completely irrelevant piece of information, a red herring sentence that had no bearing on the final answer. The results were astonishing. Even the simple rephrasing caused a significant drop in the AI's performance. But the introduction of a red herring sentence caused what the researchers called catastrophic performance drops, with accuracy plummeting by as much as 65.7%. This experiment perfectly illustrates the brittleness of AI's mathematical reasoning. Because the AI isn't actually reasoning, it's just converting statements to operations based on patterns it has seen before. When you change the wording, you disrupt the pattern. The AI can no longer recognize the problem, and its ability to find the solution shatters. It's like a student who has memorized the answers to a test but hasn't actually learned the material. If you change the order of the questions, they're completely lost. This is a critical flaw in the current generation of AI. They lack the ability for true symbol manipulation, the kind of abstract reasoning that is the cornerstone of mathematics and computer programming. Until they can overcome this hurdle, their mathematical abilities will remain a house of cards, ready to collapse at the slightest gust of wind. But what happens when the AI doesn't just get the answer wrong, but confidently invents a new one out of thin air? One of the most unsettling behaviors of modern AI is its tendency to hallucinate. This is when an AI, with complete and utter confidence, simply makes things up. It might invent historical facts, cite non-existent scientific studies, or, in the case of mathematics, fabricate answers. These hallucinations are a direct result of the AI's predictive nature. Remember, the AI's goal is not to be correct, but to be plausible. It's trying to generate the most statistically likely sequence of words or numbers, and sometimes the most likely sequence, based on its flawed training data and lack of true understanding, is just plain wrong. In a mathematical context, a hallucination might look like a simple calculation error, or it could be something more complex, where the AI misinterprets a step in a multi-step problem and goes off on a completely wrong tangent, all while presenting its work with the confident authority of a seasoned mathematician. This is because the AI lacks an internal, rule-based computation engine, like a calculator. It can't check its own work against a set of logical rules. It's essentially flying blind, relying on its linguistic intuition to guide it through a logical minefield. And when its intuition fails, it doesn't just stop and admit it doesn't know the answer. It confidently asserts a hallucinated one. This makes it incredibly difficult to trust AI with any task that requires precision and accuracy, especially in fields like finance, engineering, and science. An AI that can't be trusted to do basic arithmetic is a long way from being a reliable tool for these critical applications. This has led many to wonder if general-purpose AIs are even the right tool for the job. Which begs the question, if you want an AI that's good at math, why not build one specifically for that purpose? The struggles of general-purpose LLMs with mathematics have not gone unnoticed by the AI community. In fact, it has spurred the development of a new class of AI models, specialists designed from the ground up to tackle mathematical and logical reasoning. One of the most impressive examples of this is Google DeepMind's AlphaGeometry. This AI was trained specifically on geometric proofs and has achieved a level of performance that rivals human experts. When tested against problems from the International Mathematical Olympiad, AlphaGeometry solved 25 out of 30, a result that is on par with the average human gold medalist. The key difference between AlphaGeometry and a general-purpose LLM is its ability to use deductive reasoning. It's not just predicting the next most likely step. It's using a formal, logical system to arrive at a solution. This is a much more robust and reliable approach to mathematics than the pattern matching of its linguistic cousins. Another promising approach is to combine the language skills of LLMs with the computational power of specialized tools. For example, by integrating an LLM with a tool like the Wolfram Alpha Computational Knowledge Engine or a Python interpreter, the AI can offload the actual calculations to a system that is designed for mathematical precision. In this scenario, the LLM acts as a kind of translator, taking a word problem expressed in natural language and converting it into a formal query that the computational tool can understand and solve. This approach has shown a dramatic increase in accuracy, with some studies showing a nearly 30% improvement over a standalone LLM. These developments are incredibly promising. They suggest that, while the current generation of LLMs may never be math whizzes on their own, a future where AI can reliably solve complex mathematical problems is well within reach. But what does this mean for the future of AI and for us? The strange case of the AI that can write poetry but can't do long division reveals a profound truth about the nature of intelligence. We've discovered that mimicking human language and knowledge is a very different thing from genuine understanding and reasoning. Large language models have shown us the incredible power of pattern matching, but they've also shown us its limitations. Their struggles with math are not a simple bug to be fixed, but a fundamental aspect of their design. They are linguistic savants, not logical thinkers. And that's okay. Recognizing these limitations is the first step towards building better, more reliable AI. The future of AI in mathematics likely lies in a hybrid approach, combining the natural language understanding of LLMs with the rigorous logical power of specialized mathematical engines. We are moving from an era of generalist AIs that can do a little bit of everything to a future of specialized tools designed to excel at specific tasks. The AI that helps you write an email will be different from the AI that helps a scientist solve a complex equation. And in this future, we may finally have an AI that can not only pass a math test, but actually understand the beautiful, intricate logic behind the numbers. If you enjoyed this deep dive into the world of artificial intelligence, be sure to subscribe and hit the notification bell for more videos that explore the fascinating intersection of technology, science, and our world. Thanks for watching.